We can use the stochastic Euler method to simulate trajectories for geometric Brownian motion. We will carry out the simulation in the interval t0, t0 plus t. We'll do that in n steps of length delta t, which we assume to be small, and we'll simulate m trajectories. The monitoring times are equally spaced in the interval t0, t0 plus capital T, and they're equal to t0 plus n delta t, where n is an index that runs from 0 up to capital N. We will use the symbol S sub n superscript m to denote the value of the simulated process in the trajectory m at the monitoring time Tn. The value of the index m runs from 1 up to capital M, which is the number of simulated trajectories. And this is the algorithm that we'll use for the simulation. Basically, it tells us that all trajectories start at S0, and then we'll use this instruction to generate the trajectories at time t1 from the trajectories at time t0. This we do by multiplying the value of the trajectory in the previous time step by these factors. From the values of the trajectories at t1, we can obtain the values of the trajectories at t2, and so on until the end point of the simulation. And we'll do that for all trajectories, the first trajectory, second trajectory, and the nth trajectory. Finally, we end up with a simulation matrix which has m rows, and each of these rows corresponds to a simulated trajectory, and n plus 1 columns, and each of these columns corresponds to a monitoring time. Remember that in the Euler method you need to use small values of delta t, so that the discretization error is small. Let's see what happens if delta t is not sufficiently small. Here we're simulating trajectories from geometric Brownian motion using the Euler integration method. We're simulating trajectories between 0 and 10 in 20 steps. That means that delta t in this case is 0.5. Remember that the Euler integration method has a discretization error associated to the fact that delta t is finite and not infinitesimal as it should be. In order to illustrate the problems with choosing a delta t that is too large, here what we've done is taken the simulated trajectories and performed an average over them. In the plot below, here in the lower part of the graph, we have plotted the empirical average over these trajectories in blue. Here we can compare the average obtained with the Euler integration method with the exact average, which is this curve in black. As we can see, there is a discrepancy between these two curves, and the discrepancy becomes larger as time evolves. This is a reflection of the discretization error of the Euler integration scheme.